It is section 1.2, Review of Linear Algebra. This section also includes some examples. I'll skip most of them. If you don't have a background on linear algebra, then try to solve them yourself. If you have any questions, let me know. Then I'll try to answer your questions. Okay, here, for two vectors of n components, n-dimensional vectors, u and v, the inner product or dot product is defined in this way. U dot v is same as u transpose v. And now here, if you multiply in this way, then u1 v1 plus u2 v2, and so on. Here now u and vn. With the summation notation, we can write in this way. The length or Euclidean norm of a vector v is defined in this way. V norm is same as square root of v dot v, so that squared terms are added and take the square root. So here, norm squared is the same as v dot v. And the distance between two vectors, u and v, is defined in this way. U minus v norm. And try to solve this example yourself. Now we have a definition for two vectors u and v in Rn. They are orthogonal if the dot product is 0. This orthogonal is practically here, geometrically, they are orthogonal and 90 degrees in each other. Okay. Here we have Pythagorean theorem. Two vectors u and v are orthogonal if and only if u plus v norm squared is same as u norm squared plus v norm squared. Okay, here from high school you learned this one. Okay, and this right triangle, this is 90 degrees, and there's A, and there's B and C. Then here we know that A squared plus B squared equals C squared. That's called the Pythagorean theorem. Now, here, the same way, okay, so I'll try to make u and v. Okay, that is a vector is now u, and now that is v. Then u plus v is exactly that one. So that is u plus v. So once it's orthogonal, then now this length squared, the summation is same as here, length squared. Exactly the same as the Pythagorean theorem you learned from high school. Okay, so once they are orthogonal, then it is satisfied. Once this one is satisfied, then now u and v must be orthogonal. Okay, the inner product can be defined as here. U dot v is same as u norm times v norm times cosine theta. The theta is the angle between u and v pictorially. If this is u, that is v, okay, u and v, then angle is a theta. Right? Okay, here, linear systems of m equations and unknowns can be expressed as the algebraic system AX equal B. So A is the metric in m by n dimensions, and now right as the B is in Rm, m components. Okay. For the system, we can make augmented system by attaching here the right hand side to A. Okay. once you make it that way, then by using elementary row operations, you can solve the problem. Here we have 3 elementary row operations: replacement, interchange, and scaling. I believe you know this one quite well. In fact, the 3 elementary row operations are the major tool for linear algebra. In most of linear algebra classes, these 3 operations would be used from the beginning to the end. This is a major tool in linear algebra. Okay. Now by using, so this system can be written as now metric vector form, and augmented metric can be made, and here we apply elementary row operations to solve the system. Okay, here we have invertible or non-singular matrices. A square matrix, here the number of rows and number of columns are the same, n by n, then we call it square matrix. A square matrix A is invertible, non-singular, if there is a matrix B such that AB and BA are identity. And once such B exists, then B is unique, so that here B, rather than B, we can use A inverse, notation A inverse. Okay, so the inverse is unique. So rather than an inverse, we can say the inverse. Okay, here on n by n matrix, A is invertible if and only if A is row equivalent to In. That means that if you apply the elementary row operations to A, then in echelon form, reduced echelon form, it becomes identity matrix. Okay, so this equivalent. Once it's invertible, then you can apply elementary row operation to make it identity. Once it becomes identity, then it is invertible also. In this case, any sequence of elementary row operations that reduces A into In will also reduce the identity to A inverse, so that we can consider this algorithm. Start with AN identity, here augmented matrix. So this is n by n matrix, and again this is identity n by n matrix, and we apply elementary row operations to make this left side identity. Then the right side becomes A inverse. Once you try to find the inverse of this matrix, and you are attaching here identity matrix and apply elementary row operations to make this left side identity, then you can get its inverse. Okay, here for 2 by 2 matrix, inverse can be gotten in this way. Here that is 1 over AD minus BC, and here change the position and change the sign in this direction. Of course, here AD minus BC should not be 0. Once it's 0, then this quantity is not defined. That means A doesn't have its inverse. A is invertible, then A inverse is also invertible, and inverse of inverse is the original one. And both A and B are invertible, then the multiplication is also invertible, and AB inverse is same as B inverse and A inverse. You have to be careful for this order. And now A is invertible, then its transpose is also invertible, and transpose inverse is same as inverse transpose. The inverse and transpose commute. And now here, once A is invertible matrix, then for each B, that is the right hand side, here, for each choice of this source term right hand side, this one has unique solution, and by taking inverse both sides, we can get the solution. So if you take here A inverse, then this will disappear, and left hand side becomes X, and right hand side is now A inverse B. Here we have invertible matrix theorem. These all are equivalent. A is invertible matrix. Now A is row equivalent to the n-dimensional identity matrix and n pivot positions, and now it's really well known the equivalent terms. And here now you may consider this one. 0 is not an eigenvalue of A. So once it's invertible, then 0 cannot be eigenvalue of the matrix. Also, determinant cannot be 0. Okay? So in fact, non-zero determinant or non-zero eigenvalue means invertibility, so that they are equivalent. Yeah. Okay, that's the end of part 1, and we'll continue in the second part. Thank you.